In this video, I introduce a regularization with stochastic transformation and perturbations for deep semi-supervised learning. Randomization plays an important role in artificial intelligence learning. Stochastic gradient descent, dropout, randomized data transformation, augmentation, and many other training techniques that are essential for faster convergence and effective generalization of the learning functions introduce some non-deterministic behavior to the learning methods. Due to these uncertainties, passing a single sample through a learning system multi-times might lead to different predictions as shown here. This input sample xi, this random transportation. The learning system uses this transformed data as input to generate different predictions as shown here. Given a training sample according to consistency assumption, a model's prediction should be the same and the random transportation of the data and perturbations to the model. An unsupervised loss function is used to minimize the mean squared differences between different passes of each training sample through the learning system. The label of a training sample is unknown to enforce this loss. Therefore, the loss function is completely unsupervised and can be used along with supervised learning as a semi-supervised learning method. A training dataset consists of n unlabeled samples, and a classifier fgxi is trained to predict a vector for the input sample I during the pass G through the learning network. Unlabeled sample xi is randomly transformed by txi for n times, then passes through the learning network and produces n predictions as shown here. The random transformation Tgxi indicates the transformation G of the input sample xi. The loss function of transformation for each unlabeled sample xi is defined as here and explained in this figure, this fk and this fg is right here, which uses to force or transform the inputs Tgxi from the same samples to generate outputs, namely compliance consistency assumption. In addition, the randomness leads to a different prediction output. The cross-entropy loss is applied to the labeled data. Mutual exclusivity loss forces the prediction vector from each unlabeled sample to have only one non-zero element. In supervised learning, each element of a prediction vector is pushed toward one hard target vector. The ST loss minimizes the difference between the predictions of multiple transformed versions of an input sample, but it doesn't impose any restrictions on the individual elements of a single prediction vector. Each prediction vector might be a trivial solution due to lack of labels. The ME loss predicts multiple conflicting categories by minimizing this objective, as explained in this figure. For K, the same to C, F is 1, otherwise F is 0. Where C is the number of classes, and the element K of fgxi is defined as here. Unsupervised regularization from unlabeled data is defined as here, which includes 2 parts. One is LME and one is LST. The decision boundary cross a high density region without unsupervised regularization as shown here. There's a boundary, there's a boundary, and there's a boundary. Decision boundary cross the low density region with unsupervised regularization as shown here. This is the decision boundary, decision boundary, and decision boundary. For more details, please check with these references. Thank you. Bye.